So in the previous video, we discussed the problem with adjacency matrix, which is we are storing a lot of data and the space that was consumed was roughly proportional to v square because we have like v rows and v columns when we are discussing adjacency matrix. So a question arises is how we can save the space, especially for sparse graphs. So for dense graph, we'll have a lot of different values. But in this case, like let's say if this, you can call this as a sparse graph because the number of edges was somewhere around 7 and the number of vertices was like 6. So it's roughly equal. But if it was a dense graph, it would be something like 6 into 6, which is roughly about 36 edges should be present if this was a spot, the dense graph. So you can see like the total number of spaces that are occupied in the in memory is roughly around like 7 non-zero spaces. And if we see the total amount of spaces, it's something like 36. So we are typically consuming like 1 upon 7 or 1 upon 5 or 1 upon v times the space, which is we are wasting a lot of space, which is we are only consuming just like 20% space in this case. And if the v is much bigger, like this number is going to get way smaller, which is if we store a sparse graph which has 100 edges and 100 vertices, you might be storing like 100 values in a matrix of size 10,000, which is you are occupying just 1% of the space. So we can fix this problem is by collapsing all these zero values, which is we can store this in the form of something called adjacency list. And how it's going to look like is you see like the eighth rows has just two values. So we have just collapsed this to form like a linked list kind of data structure that only stores the value if there's an edge. So in the next row, you saw that there was just one value 60 and the next one was 5. So we have just one value here. Another one has just 5. And the final one, the final two like D and E has two values. While if you see F, this doesn't have any out vertices. So this value is pointing to a null adjacency list. But it's still there because otherwise like you'll also encounter like this is a common bug when you program, forget about what's on the right side and you just think about what's on the left when you're inserting values. So let's discuss like if we were to implement this, like there are multiple ways to implement like this adjacency list data structure. We are going to discuss some of them like right after we discuss the common operations. But the way you can implement this adjacency list is through a lot of different ways, which is one is you can have a vector of vectors where basically each vector maps to an index. Like let's say if this was not a to f, these were just numbers. So each vector location points to a new vector that stores uh, kind of the different values or the different edges that are connected to it, and so on. Another way is you can represent this in the form of a linked list. We are going to see one type of implementation. I prefer to use like a map of vectors, but it's like really free from and flexible. Whatever you use, typically the common operations cost will roughly be the same. So let's discuss how much will it cost to find whether A is connected to B. So if we want to search whether A is connected to B, now we have to go through the entire list, which is you go to this A, like assume that's constant operation. After that, you still have to traverse and see whether A is connected to B or not. Now, we inserted this in the form that B came as the first node, but there might be scenarios where B is the last node. So we have to traverse the entire list. And this is going to take like O of V complexity because there could be maximum V vertices in this adjacency list representation, given that we are assuming there are no parallel edges. Like if there were parallel edges, there could be like more than one. But we are talking again about simple graphs. So when we are talking about simple graph, like no self loops or no parallel edges, this is going to be O of V. To be more precise, it's going to be exactly like O of out degree of V, because V is connected to, let's say, like 2 in this case. So it's going to be like O of out degree of V. The next one is adjacency, which is what are A's adjacent nodes. So in this case, like if we were to find what are A's adjacent nodes, we just have to traverse again the entire list and print each of those nodes. So it's going to consume like O of V time again. Like again, it's directly proportional to O of out degree of V, but we can also simplify this further as O of V in the worst case. Now let's talk about space, like how much space would this consume? So in our case, we might be storing this vertices in the form of a map or somehow. So that's going to consume like O of V space. And now we are only storing the edges. So it's going to consume like O of E space. So this is roughly equal to O of V plus E. Now in case of dense graph, this E was V square. So like it doesn't make sense like to store this in adjacency list or matrix, because again we land back to V square. But if this was a sparse graph, E is directly proportional to V. So we have reduced this to O of V space, which is earlier when we talked about maps, uh, the matrices, this was strictly O of V square. But in our case, for sparse graphs, it's going to be just O of V. So again, like if we were to search an element that is connected to A, we just traverse each element in this G of A, which is like we just got the maps index, or if it's a vector, it would be just something like vector of 0 or A. And then we are going to return if there's a value, like if that element is present, that means it's connected. So that's like O of out degree of V. And the other one is also O of out degree of V. The space consumed is V plus E. Also remember the fact that sparse graphs edges is equal to vertices. So this transforms to something like O of V plus V, which is again like proportional to O of V. So how we can implement this is like I'm just implementing the insertion. You can see like how we print and do other stuff on this link, but I'm just covering the core part of insertion, which is again we have these values. Now I'm representing this adjacency list in the form of map of strings and vectors of pairs, which is I have something like a data structure that takes this form, which is you have something like a map or a table. Each entry in the map maps to one row, which is like, let's say if we have A, B, and 10, what I'm going to do is I'm going to insert A as the key. The vector, the value of this key is going to be a vector that consists of a pair. So what is pairs in C++? I don't know if this is covered in programming too or not, but if you if you don't know what it is, it's basically just two elements of two different or similar data types, which is in this case you can think of it as a 2D array, an array of size 2. Like you can also have an array of size 2 or a vector. Since we just have two values, which is the to vertex and the from vertex and the weight value, we can just use this pair syntax, which is this will strictly have two values. So we can store this pair, which is b comma 10, to represent like each value in this map is representing the from, like this is the from vertex, this is 2, and this is value. So we have the from mapping to the key in the table. The to vertex is the first value of the pair, and the second value is going to be the weight. So if this was an unweighted graph, it would just be something like a vector of uh, something like vector of strings, which is, let's say if we do not want to store these keys, these weights, we can just store this as vector of pairs, and we keep pushing like different values. So let's do a quick example and make this more clear, which is in this case, what it's going to do is we are going to read these three values. Let's see the code and then do a try run, which is in our case, we are again like reading these three values, which is from, to, and weight. And now in our new data structure, which is a map of key and values, where values is a vector of pair of strings and integers, you can simplify this as well. Like it's like if you think this is a way too complicated way to implement it, you can simplify it by using like vectors of vectors. You can also implement a linked list, but I'm using this convention to just give you a flavor that you can implement this in multiple ways. So how this is going to work is, in the first iteration, it's going to copy like a, b, and 10 as the values in from, to, and weight. Now the graph is basically a map, which is we have this map. This stores a key and value. So what it's going to do is we'll start from this inner syntax, which is the inner statement. So make pair is a function that is like peculiar to C++. It creates a new pair with the value 2 and the uh, the second value as weight. So the weight is going to be like, we are just changing the weight from string to integers because we have a pair of strings and integers. You can also have a pair of strings and strings. So stoi is a function that changes an integer into a string into an integer. So what we are trying to do is we are making a new pair that has the value 2 and the that has two values, which is b and 10. So our pair would look something like this: b comma 10. Next we are going to push back this value, this new pair, into our map with this value with the key from. So the graph with the value, or with the key from, is going to be a. So we are going to push this key a, and at that particular value we are going to insert a new pair that's going to be like b and 10. So our new map looks something like this. Next we are also going to insert, like since graph from was like totally empty, so the graph from will create a new key value, like even if it was not there. But what happens to this two vertex, which is we also have this two vertex, and we want to push that to create a new row for the adjacency list, which is in this case we are checking whether like in the previous way when we implemented the matrix, we did this operation, right? Like if the vertex is not present, we still want to create a mapper to that particular vertex. So in this case what I just did was I'm checking whether this vertex is already there in the graph. Otherwise, I'm going to add a new kind of a row into a table, which will look something like this. Which is, since b is not there in the graph right now, it's going to point to an empty vector. Next, what we are basically doing is it will read the next value, which is in our case, the next value is going to be a, c, and 15. So we have a, c, and 15. It will create a new pair that has values c comma 15. It's going to push back this new pair at the graphs from, where the key is the from. So graphs from is graphs of a, which is this particular row, and it's going to push back this new pair into this vector, which is, this is already a vector, and we have a new value with the value c comma 15. So you can see like our graph is now looking something like this. Next, we are also checking if the graph.find, which is we are checking if this next vertex, which is the C vertex, is already there in the graph or not. If it is not there, we are again going to create an empty one, because this is going to be useful in some scenarios where you might need to print, like let's say if they were just, our graph was something just like this, there was nothing else, we just had something like this. If you were to print the, like if I asked you to print the adjacency list, you might just print this value, which is A is pointing to B and B is pointing to C, but you'll forget that B and C should also be printed. So this is really useful to add all the vertices into our map. So if you have any questions, like you can do this in multiple other ways. Like I told you, you can implement a linked list. You do not have to necessarily use maps, pairs, and strings, but this was just one way to implement this particular data structure, which is uh, implementing graphs in the form of adjacency list. So just to sum up, we saw three different ways of implementing, which is edge list, adjacency matrix, and adjacency list. Each of them have their pros and cons, and different problems might require you to implement graphs in different ways. For edge list, we saw like it was really expensive to for common operations as well as for space. For matrix, this was a bit better. And for most of the purposes that we require, like even for your project too, you're going to use this adjacency list representation, which has a lot of cost benefit in terms of both time and space. In the next video, we are going to talk about one graph API. I think I'm going to cover this right now, and then we'll talk about graph traversals in the next one. So this is a common graph API, which is, we don't want everything to be implemented in main like this. This is like bad way to do it. I was just trying to explain you how the graphs can be powered up behind the scenes. But the actual API for the graph, like this is again, like there are two static problems, one for adjacency matrix and adjacency list. So you can design your own graph that looks something like this, which is we have a graph class. The map data structures that we just discussed, adjacency list, matrix, or edge list, goes right here, which is you might have this particular part, which is how we implemented graphs right here to back up our, our graph API. Also, this class has a constructor. It's a common place that we have another constructor that initializes a graph with the number of vertices, especially for an adjacency matrix, because we need to keep a track of how many vertices are there in the graph. Some graphs also have like either data members that keep track of vertices or edges, the number of edges, while another one might have like functions to keep to return those values and stuff like that, which just count them as you go. Some common methods that are applied to graph APIs is this insert edge function, which allows you to insert edge with the from, to, and wait value. So when we discuss this, this is basically the insert edge function for the two graphs, but it's more important to make this more modular, because this is important and you want to modularize your code rather than have this in the main. The next one is bool is edge, which basically checks whether there's an edge from the from vertex to a to vertex. Get weight just returns the weight from if we have two vertices. Now here we have everything as integers. You might have like strings or other labels, so you might need to create a mapper based on your particular use case. The next one is get adjacent. So in this one, you return a vector of the different graph vertices that are connected to a particular source vertex. The last one is print graph, which allows you to print your graph and see. So make sure you try this, because this is going to be really helpful for your project too. Like when you are implementing project two, if you are not passing these test cases in the smaller stepping problem, you might have like later on a lot of issues when you are actually implementing adjacency list for the final project or project two. Thank you.